Hey guys, I decided to make this video because I feel like more people need to be aware of how electric motors work and the different kinds of electric motors. There are many different kinds of electric motors, and the types that I talk about in this presentation are not the only kinds that you will see out there that exist. Mainly what I'm talking about are the most common types, and the one that I'm going to focus on is the one that I think that we should be using for our go-karts and all of our vehicles. And I'll back up that claim and why I think that. I talk about other motors just so that everyone is aware of what they are and their advantages and disadvantages. But anyways, let's go into the presentation. So do a little slideshow thing from beginning here. Oh, that went onto my other screen. How do I do this? That didn't work either. Taha. Okay. All right. So electric motor principles. Ta-da. Okay. So basically we have two different kinds of constructions of motors. Well, when it talks about the power that goes into them, you have AC and DC. I don't really know why. So brushless DC motor and stepper motors are technically AC motors if you look at their waveforms, but they're under the DC motor category whenever you do research on them. I'm not really sure why that is. I really think that the brushless DC motor should be called just a regular AC motor because that's basically what it is. It's just like a permanent magnet AC, whereas the brush DC is a permanent magnet DC motor. But we'll go into what these are. So a brush DC motor, if I go on to the next slide, is on the far left. And basically you have brushes that are on the commutator that go to contact patches. And as the motor spins, the contact patches change, and that causes rotation because the electromagnets are constantly in the opposite polarity or same polarity depending on the position that we desire the motor to be in, whether we want the rotor to be pushed or pulled. The difference between pushed and pulled is absolutely none. It's equal in both directions. So the bad thing about DC motors is that they have very low efficiency. Even a high efficiency DC motor, you'll see efficiencies around 88%. And the reason why is because there's a lot of energy loss around the brushes. You don't ever have perfect contact, even though there are springs that are there. And you also have the possibility for arcing. Actually, you don't have the possibility. There is arcing that happens with brush motors. And that causes for loss of efficiency. They also have very low accuracy because there's no control. It's basically just on or off. In order to control the speed of them, what we do is just send them a lower voltage. And that's basically the only kind of control that you have. One thing that I do want to point out about brush DC motors is that they do not like overvoltage. Overvolting a brush DC motor is definitely a no-go. The brushes will wear out faster, and there's just going to be a lot more arcing inside that case. Another thing with a brush DC motor is that there is no regen at all, and that has to do with how the motor spins. Because it is the poles of the motor are always set on those commutators and brushes, you're not able to do reverse current through that. Yeah. Now, with a brushless DC motor, they apply mostly in our situation. Now, we have been calling these AC motors for the longest time, permanent magnet AC motors. I really feel like that's what they should be called, but when you go on the internet, these are mainly called brushless DC motors. If you look here, the brushless DC is in the middle. That is a Y configuration, which we're going to go into later. And you'll see that it actually uses current going in both directions. And in order to drive up the efficiency, instead of using a square wave, you can use a sine wave. And then technically it would be a three-phase AC motor. So I don't know why people even call these a DC motor, but that's what they're called. So the great thing about these is that they're very efficient at all loads, because depending on the rotor position, the windings, the magnetic windings, can adjust their values based on the motor position. Whereas with the brush DC motor, it's only a square wave, and there's a lot of efficiency loss. And this area right here, you see maximal motor torque is around this area right here. So this, from here to there, you're losing a lot of the motor torque that you would normally get. And when you actually look at the torque output of a brush DC motor, you'll see that it's not linear. It actually has a lot of variation in it, or noise is a better way to put it. But with a brushless DC motor that's run off of a true sine wave, you'll see that there's barely any noise inside the torque, and it's very efficient. Actually, those are so efficient that they can make almost next to no noise, which is really cool. That's where you get silent electric cars. They also have a very high torque to weight ratio. This comes from them not having brushes or anything like that, and just the construction of the motor is the simplest out of all the other ones, which also makes regen the easiest to understand, which we're not going to go into how regen works for this presentation. Basically, well, I might as well. So how regen works is that the pieces of the the wires on the motor, instead of being powered and connected to a battery, instead they're connected to a load, and the load is recharging the battery. And basically that just causes the motor to slow down, because of it. Instead of putting energy into the motor, now we're taking energy out of the motor. So before we're going from electrical to mechanical, and now we're going from mechanical to electrical. So that's the simplest way to put it. It gets a little bit more complicated than that, but we're not going to worry about that right now. Now with the stepper motors have the highest amount of holding torque, and the reason why is because they have these teeth right here, and the teeth keep it from stepping from one place to another, and it actually requires a very high amount of torque in order for it to skip a step. Generally, those will operate at slower speeds, so that they can keep track of the steps. If one has a feedback sensor on it, then it would be able to go at higher speeds, but generally you'll see them at lower speeds. They are the most accurate because of the little tiny stators. I mean, you can just look at it and see why it's accurate. I'm not going to go into the specifics of how that one works. If you want to, you can take Dr. Marshall's class, or just an electric drives class. I learned how that motor worked in fundamentals of mechatronics, but I think that you can also take electric drives as well. One of the downsides to a stepper motor is that they're costly, and another thing is that I've never seen regen on these guys. There's not really any reason to do regen. Typically, they don't spin that fast, so you need speed in order to make regen. So, yeah. Now on to AC motors. Basically, there's two kinds of AC motors: synchronous and unsynchronous. Unsynchronous are the induction motors, and the reason why they're called unsynchronous or asynchronous or something like that is because the rotor actually moves slower than the magnetic field. I didn't go over what a rotor and stator is. I mean, I guess you can just look at these pictures, but the rotor is the part that spins and the stator is the part that doesn't spin. It's not that complicated. So we'll go over here and we'll see this is the AC induction motor. And how it works is that you have a spinning magnetic field that's made by these coils. And generally, those coils are interwoven together like a lot. Like typically, each coil will span 120 degrees over the motor. So this coil connects to probably like that coil, and then the next one would connect to the one after that. And the reason why they're so overwound next to each other is so that you can get this very, very even magnetic field that spins. And as the magnetic field spins, it induces a current inside of the rotor, which then begins to produce its own magnetic field because of the difference in the speed of the magnetic fields. Now, torque cannot be generated in this motor unless there is a difference in the speed of the magnetic field in the stator and the speed of the magnetic field in the rotor. So that's why the rotor spins slower than the magnetic field in the stator. Also, if you apply more load to a rotor, and this in an induction motor, it will spin more and more slowly the more and more load that's put on it. Yeah, and then we'll go back to the rest of the positives and negatives. They're pretty cheap. The reason why is because they're used for a lot of industry. Industry likes them because they're durable. Unlike permanent magnet motors, the permanent magnets lose their magnetism over a long period of time, like a really long period of time, like probably, I don't know, 10 years. But I mean, some electric motors inside industries are used much longer than 10 years. Especially very large ones can be used 50 plus years. One of the bad things about AC induction motors is they have a low starting torque, and there's actually a small solution to that later on in the presentation that I might mention if I remember it. One of the positives for industry but negative for us is that they have high efficiency at a high load. When let's just pick a scenario. Let's say a pump, for example. So let's say we have a gigantic pump that is pumping 2,000 gallons of water a minute into the water system. Well, that is going to be a pretty large load, and they tend to have a higher efficiency with higher loads, just because of the induction stuff. But for our situation, we have a high load only while we're accelerating. But then as soon as we get to staying at a constant speed, then the efficiency will drop for us when we use an AC induction motor. Another reason why I am not for using an AC induction motor is because they're difficult to control. As I said earlier, the rotor spins at a different speed than the stator magnetic flux rotation. So being able to control that in an efficient manner is a lot harder than it would be with a brushless DC motor. Now, if someone wants to go in and look at AC induction motors that might work for our kart, you know, I'm not going to be against it. Well, okay, I'm not going to lie, I would be against it, but there might be some out there. You know, I'm not going to put the idea out there. But don't use brush DC, stepper motor, or synchronous AC for the drive of our car, especially not the stepper motor. That'd just be stupid. And then there is the synchronous AC motor. Those are a little confusing to me as to why people use them. But basically what I've found through my research is that they're good for like low RPMs, where you need a high amount of torque at low RPMs, because they're able to keep their RPMs constant even with a change in load. And the reason why is because, and you'll see it down here, and the reason why is because they can change the magnetic the amount of magnetism that is produced in the rotor. So you can see this is the rotor here, and this is the stator here. And I'm not like very familiar with these. I've never seen one in person. I saw one motor that I'll talk about in just a minute. But another thing that is good about these is that they have a wide range of power factor, because the power factor is adjustable. I think that comes from the thing that I was just talking about, how the DC rotor can be adjusted. Now, these require DC excitation. I found 2 sources that said that, so I'm pretty sure that that's true. But I don't really trust the internet all that much, so if someone disagrees, they might be right. They do have very low efficiency. I mean, obviously you can just look at it and see that it's low efficiency. I mean, they're literally powering the both things. That one could be a magnet. So I mean, yeah, they're losing energy. Whoops, didn't mean to do that. Hey, look, Facebook. All right, so now this doesn't cover every single type of electric motor. I did see one electric motor that was on a golf cart one time that was interesting. It had 2 contacts for its stator and 2 contacts for its rotor. And the stator had much larger windings than the rotor, had smaller windings and more winds. Excuse me. And that was a little confusing to me. The rotor was brushed, and obviously the stator wasn't brushed. So it looked like a DC motor, but it used DC in like both cases. So I think it was so that you could have like an adjustable power factor, like the synchronous AC motor does. So maybe it was like a synchronous DC motor. Oh boy. Okay. Well, anyways, I'm sure that there was a reason why they picked that, but I have my opinions, and I think that brushless DC is the best. So now we're going to get into motor feedback. So when you have a either a AC induction motor or a brushless DC motor, you really need to have motor position feedback. And the reason why is because the RPM can change versus the load. Now, there's two types of motor feedbacks. There's an encoder and a resolver. Generally, on motors, you'll find a three-phase Hall sensor, which is an encoder. There are also optical ones, which basically, instead of using magnetic forces, it uses light. And I don't know, there's probably some others, but Hall sensors and photoelectric are the most common ones that I've seen. Now, the thing that is likable about encoders is that they're very simple to use. It's basically just like an on or an off. And they're really easy to see. And if you use a three-phase Hall sensor, then it will literally match up with the three phases of your motor. Which, I mean, motors have a lot more windings than three phases, but the phases and stuff, okay. So they're easy to use. Now, with the resolver, it uses a sine cosine sensor, and how the sine cosine sensor works is right here. So either this is a magnet or it's a transformer. Now, the transformer is a lot more accurate than the magnet, but some of them use a magnet. So basically what this is just a reverse of a motor. That's literally it. So as the motor spins, it induces a current into the sine and cosine sensors, and then that causes a waveform to produce on the output. Now, with a rotor that has a transformer on it, or has an electromagnet on it rather than a permanent magnet, generally it's fed an AC signal just like this, and that is in order as like a check for the sine and cosine sensors to continually see the motor position even when it's stopped. So in order to have a magnetic induction, you have to have a moving magnetic field. So if the motor's not running with permanent magnet, then you're not going to see any voltage out on the cosine or sine sensor, which means that you're not going to know the motor position from startup, which can be kind of bad. So maybe those don't exist. I don't know. But from what I found on the internet, this kind is the most common. Now, the reason why resolvers are so nice is because they have very, very high accuracy. All you have to do is compare the sine and cosine sensors, and you can get an exact result of the position. It even gives you a exact result all the way from 0 to 360. And you ask, why isn't it 180? Well, the reason why is because at 180, the pole here, like the bottom, would be the top of here, and at 360, the bottom would be the bottom of here. So if we look at this real close, we can see right there they line up, but then on the next hump over, it's at the top and the top and the bottom and the bottom. Well, it'd be able to sense it. I'm not quite sure if this one's accurate or not. Again, I don't trust the internet. But it would be able to sense the direction, because obviously you have a positive and negative fluctuation going right here, and then it would be able to read whether it was positive or negative. So you can have a sense all the way around the motor. Now, another thing that I forgot to mention about an encoder is that sometimes, very rarely, you will find a single phase encoder. or a dual phase encoder, where basically all it gives is whether it's moving forward or backward. And typically, we don't want to use those. And the reason why is because it's very easy to skip a step. If for whatever reason, the motor controller freezes for a microsecond, which is entirely possible, given EMF, communication errors, and other things like that. And then it just doesn't read one pulse from the motor. Then now your motor is offset from what the motor controller is delivering to it, which then results in lower efficiency of the motor. So it's better to get absolute position using a 3-phase or more phases. 3-phase, as you can see right here, gives a full 180 degrees of output. So, I mean, 360, blah, 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 blah. So, yeah. This is how our Hall sensor is mounted on Avenger. We have not lined up our Hall sensor with the stator, blah, 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 rotor. So, if someone wants to do that, that'd be really cool. It probably wouldn't be too hard. You just need an oscilloscope, which I guess could be hard. I don't know. But the Kelly might work better with it. We don't know if the Kelly controller, when it synchronizes with the motor, if it also synchronizes the timing of the Hall sensors. We're not really sure. Which actually reminds me. So if there is a large difference in the Hall sensor output and the actual position of the motor, then the motor will jolt really bad, and that's because it's going in a direction that it's a different position, and basically the windings aren't lined up with the magnetic field, so it'll go in a different direction, which could be completely unpredictable, and that's going to cause very, very high currents coming from the motor controller, which isn't good for the motor controller or the motor, because the motor not only will produce large amounts of current, but it will also produce a large amount of how do I say, jolt or impact. Yeah, it's like a rotational impact. So it just puts stress on the chain and everything like that. If you do donuts enough in the go-kart, you'll notice that it does that. And I think the reason why is because there's we have a 3-phase Hall sensor inside our motor, and it's obviously does not get out of line with the motor, but that deals with control systems and timing and stuff like that. So now we'll get into delta Y. If everyone knows, so messing with delta Y of a motor can be risky, but Zach wanted me to include it in here because he did it to his bike, and I do think that it's kind of cool, so I would like to present it. I don't really know as much as Zach does about this stuff, but this is a chart that I found online. If you know a little bit about delta Y, or if you're an electrical engineer, you might understand that chart. So I put it in there so that you could look at it. But yeah. Now, what I want to point out with a Y configuration is that there's higher resistance in the stator, there's lower torque, but you can go at a higher speed. And I think the reason why you can go at a higher speed is because this 60 degrees turns into, this 30 degrees turns into a 60 degrees, or this, yeah, I think that's the reason why. But I'm not completely sure. You can talk to Zach and see what he says. Now, I'll go over the delta configuration, then I'll say this. So the neutral part of the wire, you can't see my finger. Okay, so the neutral part of the Y configuration is never really connected when we're talking about motor controllers. Motor controllers only have 3 phases. I guess you could connect it to battery negative if you wanted to. That might work. I'm not really sure. I don't know. There's not really a lot of current that flows through this, so I don't know. Okay, so with delta configuration, you're going to get lower resistance because the electrical path is only through one coil, whereas the Y configuration, the path is through 2 coils. So you're going to get lower resistance, you're going to get higher torque because there's more amperage that can travel through that 1 than it can through 2, and it's also more efficient because you don't have as much energy losses as you do with the Y configuration. Generally, you will see motors in the delta configuration, and if I am correct, they are this one right here. I chose one with a UVW, so you could directly connect, relate it to motors. But typically, you don't see the Y and delta configurations on motors unless it's an AC induction motor. And now I'll go into why. So with an AC induction motor, typically they are wired as a delta. But during startup, they require large amounts of current in order to induce a field into the stator, because they don't have magnets inside the stator, the rotor, to induce a field into the rotor. So typically, that's going to decrease the life of your induction motor, and further and so on. And you also need that startup to travel at a very high speed. So typically what they do is at the very start of an induction motor, they use a Y configuration. And the reason they do that is because it's going through 2 windings, it can handle more torque. Excuse me. And it also rotates at a higher speed, so it induces the current into the rotor faster. So that's why the AC induction motor switches between Y and delta. Now, I would not recommend changing the Y or delta of a motor, and the reason why, okay, anyways. The reason why is because the Y configuration produces higher voltage higher induction voltage inside your windings, which can cause arcing and insulation breakdown. Whereas your delta configuration, if your motor is configured as a Y, your delta configuration will produce more current inside your motor, which will reduce the lifetime of it, and it could possibly overheat. When designers of motors make the motors, they specifically pick a wire size, insulation thickness, and a number of turns and stuff like that, so that it can handle the rated current and the rated volts that happen inside the motor. And if we change that configuration, then what can end up happening is we can damage our motor over time, because we're putting more stress on the motor than what the designer intended, whether that be volts or amps. So yeah. Now, I'll go into the motor case, and I think that this is, nope, we got one more. Okay, so When it comes to motor cases, these next two slides are very, very important. If we are able to get a motor that is an outrunner, outrunners are much more efficient than in-runners. Well, actually, I need to rephrase that because I do have more efficient under in-runners. For us, outrunners are better, and I will go into why. So in runners, magnets are positioned on the inside. The permanent magnets, so these, starting from the Y versus, well, actually starting from the motor case and the axial flux, I'm only talking about brushless DC, or as I call them, AC motors. So with end runners, the magnets are connected. The magnets are always connected to the rotor. With end runners, the magnets are inside the coil windings. So basically, the case of the motor stays still while the axis of the motor rotates. What that ends up doing is that the motor is able to spin at a higher RPM because there's less mechanical, the radius of the mechanical components on the inside is lower, which means that there's less chance of failure for a higher RPM. Now, this is good for electric motors, and it's a lot more efficient because electric motors like spinning at very fast RPMs. The higher RPMs you get, the less mechanical resistance that you get, and the less energy losses that you get. So that is why end-runner motors are more efficient, because they operate at a higher RPM. Now, the downside for end runners for us is that a higher RPM means a higher gear ratio. It is very, 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 very rare to find an electric motor that spins at the same or less RPMs than the wheels. That has to do with just magnetic flux is not as strong as the amount of force that we want to put on the tire. So generally we ramp up the RPMs and then we have higher torque. Yeah, basically. Now, if end runner motors typically have RPMs close to, like, I don't know, 8,000 might be the minimum. At 10,000, you could probably get 12,000. I don't know. There's a lot out there. If you've done a lot of searching on motors, you probably know what I'm talking about. But in order for us to do a gear ratio for, let's say, 10,000 RPM, we're literally going to have a gear ratio of 4:1 or higher, which means that we can't go just from one sprocket to another. We have to actually use a gearbox. Trust me, you don't want to use a gearbox. First off, it's going to lower our efficiency a lot more than the efficiency that we would gain from using a higher RPM motor. And there's more mechanical parts, so there's more points of failure. So that's why we really, really need to find a motor that's within the RPM of sprockets that we can use. Now, those sprockets that we can use are based on the tire diameter, because you obviously can't have a sprocket bigger than the tire diameter, and the minimum diameter of a sprocket that we can put on the shaft of the motor. So that depends on our change size, actually. And obviously, if we're producing a lot of torque, we want a big chain size, which means that our tiny gear has to be a little bigger. But anyways, so outrunner motors means that the magnets are on the outside, which I've already said. But they have more torque. And the reason why they have more torque is because the magnets are on the very outside of the motor. So if anyone's ever taken physics, dynamics, statics, even if you've passed high school, you know that if you spin the very outside of your steering wheel of the car, you're going to have more force on the wheels than if you spin the inside. I mean, yeah. So that's why they have more torque. And then one of the negatives is that they have a higher moment of inertia, which the moment of inertia, when it comes to a go-kart or a car, relates to the acceleration of a car. So if you have a very high moment of inertia on a car, you're actually doubling the amount of weight that's put on the car. So let's say that you're trying to push a 200-pound car with a I don't know, these calculations aren't going to add up, but a 20 pound moment of inertia thing. So then what you're actually pushing is the moment of inertia of the rotational components and the weight of the rotational components. Now, when it comes to an outrunner motor, the amount of torque that we get out of the motor more than compensates for the higher moment of inertia. So we really don't have to worry about the higher moment of inertia on the motor. It's just, I just threw that in there because I think that it's important. Another thing is that they have smoother operation. And the reason why is you can have more magnets and more windings. There's just more space. And they also have better cooling. If you'll notice on the end-runner motor, there's not as many air gaps. And the reason why is because there's nothing like actually just, spinning the air. Typically, if you see an end-runner motor, they're going to have a fan attached to the rotor. And the reason why is because they have to cool it somehow. I mean, I guess they don't have to, but you really should. But the outrunner motors, the case actually cools it, which is really cool because if you know how a fan works, or a radial fan, I think is what they're called. Basically, the motion of the case spinning will actually cause air to be flinged out of the motor, which is the best way that I can describe it. So that's why outrunner motors are so much better than end-runner motors. So now I'll go into the flux direction. If you have not taken Physics 2, flux might be like, I don't know, Magic Cosmos or shit that can't remember that guy's name. Morty, Rick and Morty. So stuff that Rick does. Flux, basically, just think about like magnetism if you don't know what it is. So inside most motors, you'll find radial flux. Now, radial flux is good for packaging, but that is really the only good thing about it. They have a longer construction to their motors, and that's the only thing that's good about them is the packaging. But when you look at a radial flux motor and you compare it to an axial flux motor, you'll see that axial flux motors have magnets on both sides, which is awesome. They have magnets on the back and they have magnets on the front, whereas radial flux only has magnets on the outside. Now, this is a really good lesson in geometry. Radial is pointing outward from the axis, and axial is going rotating around the axis, or pointing along the axis. Yeah. Okay. So the axial flux that happens in a radial motor actually goes, it starts out here in this magnet, and then it goes down, and then it has to actually bend and come back inside this magnet and go electromagnet and come out to this permanent magnet right here. And then the permanent magnets have some flux that happens across themselves. Now here, the axial flux goes from this magnet straight through the electromagnet and then right into the magnet right after it. And then the magnets have some flux that goes right here. So the path of a radial flux motor is very direct, which is good because the lower the flex path, the stronger it is. Basically, that's the best way I can describe it. Now, an axial flux, I put wider, but wider isn't very accurate. It's a larger diameter, and the reason why is because of the construction of it. Generally, you want your coil to not be very long, because the very center of your coil is affecting the magnets a lot less than the very outside of your coil, outer edge of your coil. So that's why they have a short length and a large diameter. They have a much higher power density, and I mean, I've already talked about that. The power density comes from the flux direction. And another thing about them is that they have much better cooling. And the reason why, even with this being an outrunner motor right here, and this can be an end runner or an outrunner motor, basically, when this is rotating, the magnets get in the way of air coming out of the motor. But in here, we can put holes all along the case, and then the air is able to go in through the center and come out through the sides, which allow for much better cooling, because all of the air is literally going across the coil windings. Well, I mean, yeah, they're going across the coil windings here, but oh, whoops, I did it again. Oh crap. I want to get back to that slide. I was on such a roll. But you'll see here that if you look closely, this is a radial flux. And on our motor, the MRAX 228, it's an axial flux motor. And you'll see these holes right there, and those holes are for cooling. But oh crap, well, fine, I'll just pull it over here. On this motor, they can't put holes in there because there's magnets there. So, you know, better cooling means that you can put more current through it, and ultimately you'll get more power. So, yeah, in pretty much all cases, axial flux is better. Now, the reason why you don't see as many axial flux out there is because it's still relatively new. Now you ask the question, why is it new? I mean, it seems pretty simple to me. I have no idea. I think it seems pretty simple. If I was the leader in designing a really powerful electric motor, I would think about electromagnets going in every which way. But you know, I don't know. Whoever invented this was a genius, because it's really awesome. So that's basically my presentation on electric motors and selections of the properties. This does not have to do with calculations. I am going to do another presentation on calculations, but first I need to verify my calculations to make sure that they're 100% correct and that they make sense. So I just want to go over a brief overview. So in my opinion, brushless DC motors are the best, but if you want to look at brush DC or AC induction, you know, it's probably worth it. But brushless DC is the best, or AC, as I call it. Resolver feedback is the best, but encoders work just fine. Delta configuration is the best, but you're probably not going to see that on a data sheet. The outrunner motor is the best. The easiest way to tell if it's an outrunner is typically the case looks like it spins, and typically the case has wider openings than a case that doesn't have an outrunner. And it will probably say outrunner because people like outrunners. And then another thing is axial flux. Always, always, always do axial flux. And typically, when you look at an axial flux motor, it's going to be it's going to be like this kind of construction as our MRAX is. Now, one more thing that I want to bring up is that this is a difference that someone found in wind turbines of the difference between an axial flux motor and a radial flux motor for a wind turbine. You can just see the difference in weight and the difference in axle length. Obviously, axle length isn't mostly what we care about, because axle length would actually be better for us because it's better packaging, but the weight is substantial. The weight savings, that's like more than quadruple. I mean, you know, but anyways, so have a good night, and hope you enjoyed the presentation. So bye.